Terraforming of a planet, moon, or other body is the hypothetical process of deliberately modifying its atmosphere, temperature, surface topography or ecology to be similar to the environment of Earth to make it habitable by Earth-like life. The concept of terraforming developed from both science fiction and actual science. The term was coined by Jack Williamson in a science fiction story published during 1942 in Astounding Science Fiction, but the concept may predate this work. Based on experiences with Earth, the environment of a planet can be altered deliberately. However, the feasibility of creating an unconstrained planetary environment that mimics Earth on another planet has yet to be verified. Mars is usually considered to be the most likely candidate for terraforming. Much study has been done concerning the possibility of heating the planet and altering its atmosphere, and NASA has even hosted debates on the subject. Several potential methods of altering the climate of Mars may fall within humanity's technological capabilities, but at present the economic resources required to do so are far beyond that which any government or society is willing to allocate to it. The long time scales and practicality of terraforming are the subject of debate. Other unanswered questions relate to the ethics, logistics, economics, politics, and methodology of altering the environment of an extraterrestrial world. History of scholarly study. Carl Sagan, an astronomer, proposed the planetary engineering of Venus in an article published in the journal Science in 1961. Sagan imagined seeding the atmosphere of Venus with algae, which would convert water, nitrogen, and carbon dioxide into organic compounds. As this process removed carbon dioxide from the atmosphere, the greenhouse effect would be reduced until surface temperatures dropped to comfortable levels. The resulting carbon, Sagan supposed, would be incinerated by the high surface temperatures of Venus, and thus be sequestered in the form of graphite as some involatile form of carbon on the planet's surface. However, later discoveries about the conditions on Venus made this particular approach impossible. One problem is that the clouds of Venus are composed of a highly concentrated sulfuric acid solution. Even if atmospheric algae could thrive in the hostile environment of Venus's upper atmosphere, an even more insurmountable problem is that its atmosphere is simply far too thick. The high atmospheric pressure would result in an atmosphere of nearly pure molecular oxygen, and cause the planet's surface to be thickly covered in fine graphite powder. This volatile combination could not be sustained through time. Any carbon that was fixed in organic form would be liberated as carbon dioxide again through combustion, short-circuiting the terraforming process. Sagan also visualized making Mars habitable for human life in Planetary Engineering on Mars, an article published in the journal Icarus. 3 years later, NASA addressed the issue of planetary engineering officially in a study, but used the term planetary ecosynthesis instead. The study concluded that it was possible for Mars to support life and be made into a habitable planet. The first conference session on terraforming, then referred to as planetary modeling, was organized that same year. In March 1979, NASA engineer and author James Oberg organized the first terraforming colloquium, a special session at the Lunar and Planetary Science Conference in Houston. Oberg popularized the terraforming concepts discussed at the colloquium to the general public in his book New Earths. Not until 1982 was the word terraforming used in the title of a published journal article. Planetologist Christopher Mackay wrote Terraforming Mars, a paper for the Journal of the British Interplanetary Society. The paper discussed the prospects of a self-regulating Martian biosphere, and Mackay's use of the word has since become the preferred term. In 1984, James Lovelock and Michael Allaby published The Greening of Mars. Lovelock's book was one of the first to describe a novel method of warming Mars, where chlorofluorocarbons are added to the atmosphere. Motivated by Lovelock's book, biophysicist Robert Haynes worked behind the scenes to promote terraforming, and contributed the neologism ecopoiesis, forming the word from the Greek omicron kappa omicron sigma oikos house and pi omicron iota eta sigma iota of sigma poiesis, production. Ecopoiesis refers to the origin of an ecosystem. In the context of space exploration, Haynes describes ecopoiesis as the fabrication of a sustainable ecosystem on a currently lifeless, sterile planet. Ecopoiesis is a type of planetary engineering and is one of the first stages of terraformation. This primary stage of ecosystem creation is usually restricted to the initial seeding of microbial life. As conditions approach that of Earth, plant life could be brought in, and this will accelerate the production of oxygen, theoretically making the planet eventually able to support animal life. Aspects and definitions. Beginning in 1985, Martin J. Fogg began publishing several articles on terraforming. He also served as editor for a full issue on terraforming for the Journal of the British Interplanetary Society in 1992. In his book Terraforming, Engineering Planetary Environments, Fogg proposed the following definitions for different aspects related to terraforming. Planetary engineering: the application of technology for the purpose of influencing the global properties of a planet. Geoengineering: planetary engineering applied specifically to Earth. It includes only those macroengineering concepts that deal with the alteration of some global parameter, such as the greenhouse effect, atmospheric composition, insolation or impact flux. Terraforming, a process of planetary engineering, specifically directed at enhancing the capacity of an extraterrestrial planetary environment to support life as we know it. The ultimate achievement in terraforming would be to create an open planetary ecosystem emulating all the functions of the biosphere of Earth, one that would be fully habitable for human beings. Fogg also devised definitions for candidate planets of varying degrees of human compatibility. Habitable planet: a world with an environment sufficiently similar to Earth as to allow comfortable and free human habitation. Biocompatible planet: a planet possessing the necessary physical parameters for life to flourish on its surface. If initially lifeless, then such a world could host a biosphere of considerable complexity without the need for terraforming. Easily terraformable planet: a planet that might be rendered biocompatible, or possibly habitable, and maintained so by modest planetary engineering techniques and with the limited resources of a starship, a robot precursor mission. Fogg suggests that Mars was a biologically compatible planet in its youth, but is not now in any of these three categories, because it can only be terraformed with greater difficulty. Mars Society founder Robert Zubrin produced a plan for a Mars return mission called Mars Direct that would set up a permanent human presence on Mars, and steer efforts towards eventual terraformation. Habitability requirements: an absolute requirement for life is an energy source, but the notion of planetary habitability implies that many other geophysical, geochemical, and astrophysical criteria must be met before the surface of an astronomical body is able to support life. Of particular interest is the set of factors that has sustained complex, multicellular animals in addition to simpler organisms on this planet. Research and theory in this regard is a component of planetary science and the emerging discipline of astrobiology. In its astrobiology roadmap, NASA has defined the principal habitability criteria as extended regions of liquid water, conditions favorable for the assembly of complex organic molecules, and energy sources to sustain metabolism. Preliminary stages. Once conditions become more suitable for life of the introduced species, the importation of microbial life could begin. As conditions approach that of Earth, plant life could also be brought in. This would accelerate the production of oxygen, which theoretically would make the planet eventually able to support animal life. Prospective planets. Mars. In many respects, Mars is the most Earth-like planet in the solar system. It is thought that Mars once had a more Earth-like environment early in its history, with a thicker atmosphere and abundant water that was lost over the course of hundreds of millions of years. The exact mechanism of this loss is still unclear, though three mechanisms in particular seem likely. First, whenever surface water is present, carbon dioxide (CO2) reacts with rocks to form carbonates, thus drawing atmosphere off and binding it to the planetary surface. On Earth, this process is counteracted when plate tectonics works to cause volcanic eruptions that vent carbon dioxide back to the atmosphere. On Mars, the lack of such tectonic activity worked to prevent the recycling of gases locked up in sediments. Second, the lack of a magnetosphere around Mars may have allowed the solar wind to gradually erode the atmosphere. Convection within the core of Mars, which is made mostly of iron, originally generated a magnetic field. However, the dynamo ceased to function long ago, and the magnetic field of Mars has largely disappeared, probably due to loss of core heat, solidification of most of the core, and/or changes in the mantle convection regime. Mars does still retain a limited magnetosphere that covers approximately 40% of its surface, rather than uniformly covering and protecting the atmosphere from solar wind. However, the magnetic field takes the form of a collection of smaller, umbrella-shaped fields, mainly clustered together around the planet's southern hemisphere. It is within these regions that chunks of atmosphere are violently blown away, as astronomer David Brain explains. The joined fields wrap themselves around a packet of gas at the top of the Martian atmosphere, forming a magnetic capsule 1,000 kilometers wide with ionized air trapped inside. Solar wind pressure caused the capsule to pinch off, and it blew away, taking its cargo of air with it. Finally, between approximately 4.1 and 3.8 billion years ago, asteroid impacts during the late heavy bombardment caused significant changes to the surface environment of objects in the solar system. The low gravity of Mars suggests that these impacts could have ejected much of the Martian atmosphere into deep space. Terraforming Mars would entail two major interlaced changes: building the atmosphere and heating it. A thicker atmosphere of greenhouse gases such as carbon dioxide would trap incoming solar radiation. Because the raised temperature would add greenhouse gases to the atmosphere, the two processes would augment each other. Venus. Terraforming Venus requires two major changes: removing most of the planet's dense 9 megapascals carbon dioxide atmosphere and reducing the planet's 450 degrees Celsius surface temperature. These goals are closely interrelated, because Venus's extreme temperature is thought to be due to the greenhouse effect caused by its dense atmosphere. Sequestering the atmospheric carbon would likely solve the temperature problem as well. Other bodies in the solar system. Other possible candidates for terraforming include Titan, Callisto, Ganymede, Europa, the Moon, and even Mercury. Saturn's moon Enceladus and the dwarf planet series. Paraterraforming, also known as the world house concept, or domes in smaller versions. Paraterraforming involves the construction of a habitable enclosure on a planet which eventually grows to encompass most of the planet's usable area. The enclosure would consist of a transparent roof held 1 or more kilometers above the surface, pressurized with a breathable atmosphere, and anchored with tension towers and cables at regular intervals. Proponents claim world houses can be constructed with technology known since the 1960s. The Biosphere 2 project built a dome on Earth that contained a habitable environment. The project encountered difficulties in operation, including unexpected population explosions of some plants and animals, and a lower than anticipated production of oxygen by plants, requiring extra oxygen to be pumped in. Ethical issues. There is a philosophical debate within biology and ecology as to whether terraforming other worlds is an ethical endeavor. From the point of view of a cosmocentric ethic, this involves balancing the need for the preservation of human life against the intrinsic value of existing planetary ecologies. On the pro-terraforming side of the argument, there are those like Robert Zubrin, Martin J. Fogg, Richard L. S. Taylor and the late Carl Sagan who believe that it is humanity's moral obligation to make other worlds suitable for life, as a continuation of the history of life transforming the environments around it on Earth. They also point out that Earth would eventually be destroyed if nature takes its course, so that humanity faces a very long-term choice between terraforming other worlds or allowing all terrestrial life to become extinct. Terraforming totally barren planets, it is asserted, is not morally wrong as it does not affect any other life. The opposing argument posits that terraforming would be an unethical interference in nature, and that given humanity's past treatment of Earth, other planets may be better off without human interference. Still others strike middle ground, such as Christopher McKay, who argues that terraforming is ethically sound only once we have completely assured that an alien planet does not harbor life of its own, but that, if it does, we should not try to reshape it to our own use, but we should engineer its environment to artificially nurture the alien life and help it thrive and co-evolve, or even coexist with humans. Even this would be seen as a type of terraforming to the strictest of ecocentrists, who would say that all life has the right, in its home biosphere, to evolve without outside interference. Economic issues. The initial cost of such projects as planetary terraforming would be gargantuan, and the infrastructure of such an enterprise would have to be built from scratch. Such technology is not yet developed, let alone financially feasible at the moment. John Hickman has pointed out that almost none of the current schemes for terraforming incorporate economic strategies, and most of the models and expectations seem highly optimistic. Political issues, national pride, rivalries between nations, and the politics of public relations have in the past been the primary motivations for shaping space projects. It is reasonable to assume that these factors would also be present in planetary terraforming efforts. In popular culture, terraforming is a common concept in science fiction, ranging from television, movies and novels to video games.